Alright, so we're mostly right or mostly wrong. If you think this is true, somebody want to volunteer the rationale for me? Alright, what if it's false? If it's false, what's your rationale? How would it be used again? Do that again?
Put it back on.
Yeah, we gotta remake our ATP. Remember, ATP gets recycled. That's exactly right. Right, so ATP, we're gonna hydrolyze it to make ADP plus P. What do we liberate as a part of this process?
Energy.
And what do we do with that? Use the power of what? Yeah. I.e. all the different types of cellular work. But once we've spent it, we can put it back together. But that's going to take energy. Where's that energy coming from?
Another reaction.
Where do we get the energy to stick A, D, P, and P back together? I'm going to transform energy from one form into energy in the form of ATP. Ooh, I'm glad I asked this question. Not this one. This is a thinker. It's about 2 o'clock. Probably did this within the last 2 hours.
Catabolic.
You
Eat.
what do you do about noon? You eat. Why? Right? You need energy. So your food is providing the energy, right? We're going to transform the energy in your food molecule into energy in the form of ATP. And then we're going to use that energy, now that it's in a form that our cell can use, to do some work. But now I'm stuck with this. And I need some more of that. So what do? I use some more of the energy from my food to stick these back together. Alright, so it's not usable in this form for providing energy, but right, we're recycling ATP all the time. A single muscle cell is recycling roughly 10 million ATP per second. Right? So you got a lot of this going on. Kathy, your hand might be. Oh, I think you're good. You're good. That works, Valerie. All right, everybody on the board? Ever? Yeah, it's not having any of that. There he goes. All right. Okay, first of all, what are enzymes? Catalysts, but they're special kind of catalyst. They're biological, right? They're organic. They are made out of, they're proteins. Okay, so what do you know about proteins? You learned all about their primary, secondary, tertiary structure. Are all proteins the same? No. So why are they different? They all have their own unique structures. They have their own unique sequence. So they're going to be specific, right? They're only going to interact with a specific substrate because they have a specific structure. Are catalysts used up in a reaction or changed? No, so they should be reusable, right? Same catalyst can work over and over and over again because It's not changed by the chemical reaction. Do they add energy? No. So this is our answer, right? Do they lower activation energy? Yeah, that's the primary thing they do, right? That's the magic. That's how they are able to speed up a reaction. But what they're not doing is adding energy, which ought to make this next question really easy.
There it is, I think.
Always right on the edge. There we go. All right. All right, I just asked you the same question in a slightly different way. So, do they provide a favorable microenvironment? Yes. Do they provide the energy necessary for reaction to begin?
Yes.
No, they're not adding energy in, they're lowering the amount of energy required, right? They're lowering the activation energy. Do they orient the substrates correctly?
Yep.
Yeah, absolutely. Remember I was showing you the markers?
Yep.
Example, and I said we could just let them randomly collide until they just happen to hit each other at just the right angle and just the right amount of energy to connect, or I could just say grab, or oriented correctly, make the bond. Right? Straining substrate bonds. Right? The most unstable state is when those bonds are the most strained. So if I was going to, for example, break the bond here, right, my job as an enzyme is to strain that bond so that it doesn't take as much energy for this reaction to take place, because this is a really unstable state. Remember our graph, right, where this is energy and this is reactants, products. Right, this is our activation energy. Right, the top of that hump is where we have the most strain in the bonds of our molecule. That's the most unstable state. We call this the transition state. So another way to sort of phrase this is to say that an enzyme is going to promote the transition state. What that means is if I'm going to break these bonds, the transition state means I'm helping sort of already strain it this way. If I'm putting them together, right, it's the same sort of thing. The bonds are going to be strained before they finish forming, right? So I'm still promoting the exact same transition state. It's just that I'm helping make that bond instead of breaking. Right? So enzymes are going to promote the transition state, but it's going to take less energy to get there. So it's going to be a lower activation energy. Yeah?
What does the EA stand for?
Activation energy, or energy, if you want to put it this way, of activation. I think sometimes it's phrased that way, which is why it's E sub A. Questions? All right, so we got to catch up on a bunch of business, and then we'll get started. So first, let's see. How many of you guys worked on the cell transport worksheet that I posted up? 1, 2, 3, 4. I know somebody was asking me questions, like maybe 5. Okay, 6. All right, so I published the key to that. Right? I still highly recommend that you work through that worksheet before you look at the key. right? The worksheet is designed to sort of lead you by the hand, thinking-wise, question by question, to sort of analyze what's happening in these different examples of transport. So if you just look at the key, it's not really gonna help you much. All right, so that's posted under the membrane structure and function module. Let's see, next up, energy and enzymes. You may find these particularly helpful. What else was I gonna show you? I think that's it for old stuff. Oh, and then DNA replication, which hopefully we'll jump in today. There's a worksheet here. Again, it's sort of like draw a diagram illustrating what's happening for a particular step during DNA synthesis. I'll just leave the key there, right? So once again, I would spend some time sort of going through the notes, use that as your template to go and draw out this, and then double check your answers. That'll be particularly helpful in preparation for the exam. All right, so I sent out an announcement yesterday. I sent you guys the correct new instructions, so if you had downloaded them out of the announcement that I sent you, you would have had the right thing. But there was a link that didn't get fixed, and the old document was still posted. So if you don't have not that one. I don't care about design, I don't care about SDS page. I don't care about slides. I care about, right, so the ideal SDS page results here, along with some descriptions. And then the mini report guidelines are here. And I know I said this to my section, but there should be like check boxes for each thing, right? So you're checking it off as you go. So if you had like little round dots, that's the old version. So what you were supposed to have, and I apologize, I thought that link had been taken out. At the end of this, right, that's a lot of stuff. Boil it down, you're supposed to have